Hi, and welcome to XenSpace. In this episode, I'd like to talk about a high-tech quantum communication device. That, so far as I'm aware, it should work. It allows instantaneous communication across any distance, utilizing a quantum principle property called entanglement. Now, I'm sure any physicist out there will be immediately going, no, you can't do that, Zen. Instant communication is not possible. It's against the laws of physics. And maybe they're right, but bear with me. Let's see if I do explain it, it starts to make more sense. So what is this entanglement, this quantum property? Effectively, it's where two particles, take for example an electron, electrons have a property called spin. I believe it's usually referred to as spin up or spin down. So when you get two electrons entangled in this way, where it's the spin property, which is the entangled property we're looking at. Now, one should be spinning up and one should be spinning down. But while they're entangled, they're in a superposition. They're both up and down at the same time. Their state is intimately connected, and you can separate them across any distance. And as soon as you measure one of them, as soon as you break that entanglement by measuring it, if the spin up result is what you get, then the other one will spin down, or it depends how they were interrelated to start with. They might both be the same. But anyway, the issue is that as soon as you interfere with one or analyze one, the other one instantly is changed. So it goes from being in a superposition to not being in a superposition. Basically, either being spin up or spin down, it becomes one or the other of them. It's not in a superposition both. So how do you use this to communicate? Because you can't control whether it's going to be spin up or spin down. You can't use that, for example, like it was digital information, like zeros and ones. Well, it's binary information. They talk about the digital age, which is actually the binary age. But anyway, I won't go about that now. Right, so you have these entangled particles, and what you do is you trap them. I use this dice as an example. You get one trapped in this one trapped in this one. Separate them by any amount. I won't. It goes off the picture then. So you have them separated. As I say, as soon as you measure this one will the quantum particle in this one will be affected. Now, each of these traps has another two sensors in them, what I call a soft sensor and a hard sensor. The hard sensor analyzes the quantum state actively and destroys the superposition. So if the hard sensor is activated in this one, the quantum state in this one will be affected. And the second sensor is what I call a soft sensor, which doesn't directly it's just like passive. It doesn't directly interfere with the quantum state of the particle, but it will be aware when the quantum state changes. It will somehow it knows when that's happened. You know, it can detect the quantum state change from being in a superposition to not. So when the hard sensor in this one is activated, the soft sensor in this one will activate. That lets you know when this message is being sent. As I say, you can't actually send a message that way. So how do you get the message from one person to the other? Well, it's quite simple. What you do is you have, and the reason why I've used dice is because they're quite small. You could potentially stack hundreds and hundreds of these in you could get sheets, get 100 this way, 100 that way, 100 this way. So you have, what would that be? That would be 1,000, wouldn't it? You could easily get 1,000 of these set up. It wouldn't be too big. If unfortunately the trap with the sensors was the size of a TV set, for example, that would be a bit too big. You couldn't get too many of them into one array, so to speak. So yeah, what you need to do is create an array using as many of these things as you can, put into as many traps each with their two sensors. And you have pre-agreed in advance, obviously, before you separate the two machines, the two arrays. a code which tells you when a particular trap is activated, what that means. So trap number 1 is activated means X, trap number 2 activated means Y, trap 3 activated means Z, and so on. And you can have quite a complex form of communication this way, only limited by the number of traps you can fit inside the array. Why might this not be possible? Well, it all comes down to the two things really: the soft sensor, whether that's possible, if you can create a piece of equipment which can detect a superposition decaying or being broken, so that the quantum entanglement is destroyed. If you can't detect that happening, then sorry, this doesn't work. But if it does, then there's no reason why not. I mean, it might be difficult to maintain the quantum state for an extended period of time. I don't know how efficient these traps are at keeping them isolated from other effects. I mean, for example, if you communicate with only distance, you really want to communicate with far distance, because otherwise, if it's on Earth, you can phone someone. It's fairly instantaneous. So it's only if you're talking about hundreds of thousands of miles away out in space. So getting something into space generally requires quite a, how should we put it, a strenuous effort to leave the planet's gravity. So that might involve shaking and acceleration forces, which might not do the quantum state too much good. But if we put all that aside for now, how would this be used? As I say, it can provide an instant communication when you know what the messages mean, which one's been activated. But for what about other systems where you might need instantaneous communication? What might be a benefit to have such instantaneous communication? Well, one idea it seems to me is that we have an issue with solar flares. If there were a massive solar flare that hit planet Earth, it would cause havoc to our electricity and systems. The national grid and so forth would probably be fried. So all electronics would immediately be more or less destroyed. So how can we fight against that? The problem is there's no way to get any forewarning of the solar flare coming our way, because it moves at the speed of light, and nothing travels faster than the speed of light. So it leaves the sun and hits us 8.5 minutes later, or is it nearer 9 minutes, and boom, we just lost all our telecommunications and computers and everything else. But if we had one of these little devices in a probe or something, a little satellite that's kept between the sun and the Earth, then obviously when the flare hits that on its way towards us, it would probably destroy all the electronics on the probe, and that would probably disrupt the quantum state, the entangled state, destroy that, and we'd instantaneously know the probe was gone, and therefore that we have a flare on its way to us. I think that's the long and short of the idea. Obviously, there are many other ways this could be used. If we ever do get into space and have colonies on other planets, then it might be useful from time to time to synchronize. Such devices could be used to very quickly, to instantaneously that people know what the time is relevant to them. So that's probably not really that much use on a colony within the solar system. It has to be a lot further out. But anyway, my time is drawing to a close, and I need to say goodbye. So thanks for joining me. I hope that was interesting, and I'll see you next time. Cheers and take care.